moving on to the last topic of the chapter, abnormal molar masses. We know that ionic compounds, when dissolved in water, dissociate into cations and anions. For example, if we dissolve 1 mole of KCl 74.5 grams in water, we expect 1 mole each of K plus and Cl minus ions to be released in the solution. If this happens, there would be 2 moles of particles in the solution. If we ignore interionic attractions, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52 Kelvin, which should be 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles is 74.5 grams and the mass of 1 mole of KCl would be 37.25 grams. This brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. Molecules of ethanoic acid, acetic acid, dimers in benzene due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case, the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated that here that if all the molecules of ethanoic acid associate in benzene, then DDP or DDF for ethanoic acid will be half of the normal value. The molar mass calculated on the basis of this DTB or DTF will therefore be twice the expected value. Such a molar mass that is either lower or higher than the expected or normal value is called as abnormal molar mass. In 1880, Van 't Hoff introduced a factor I known as the Van 't Hoff factor to account for the extent of dissociation or association. This factor I is defined as I is equal to normal molar mass. Okay, before coming to the formula, let me tell you that through experiments they have found out that because of dissociation and association of molecules, once they have been dissolved in the water, there is a difference in the molar mass that is determined experimentally than that of the true value. Now, because of association of molecules, there is a difference. That is, either the molar mass is lower or higher than the expected or normal value, and that is called as the abnormal molar mass. Now, Van 't Hoff introduced a factor I and he named it after him as Van 't Hoff factor to account for the extent of dissociation or association. This I has been given three formulas. First one is normal molar mass by abnormal molar mass, or observed colligative property by calculated colligative property, or total number of moles of particles after association or dissociation by number of moles of particles before association or dissociation. Here, abnormal molar mass is the experimentally determined molar mass, and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. So, generally we are taking the colligative properties to have we are assuming that we are calculating colligative properties by assuming that the non-volatile solute is neither associating or dissociating. In case of association, value of I is less than unity, while for dissociation it is greater than unity. For example, the value of I for aqueous KCl solution is close to 2, while the value for ethanoic acid in benzene is nearly 0.5. In conclusion, inclusion of Van 't Hoff factor modifies the equations for colligative properties as follows. The first one, relative lowering of vapor pressure, P1 naught minus P1 by P1 naught is equal to I into N2 by N1. Elevation of boiling point is delta TB is equal to I KBM, that is molality. Depression of freezing point is delta TF which is equal to I, that is Van 't Hoff factor, into Kf into molality. Osmotic pressure of solution is nothing but osmotic pressure is equal to I into N2 RT by volume. Now, this osmotic pressure formula would be important. That is, when they are asking about the osmotic pressure of the solution, maybe they might give you the osmotic pressure and we'll have to find the Van 't Hoff factor, or we'll have to know the Van 't Hoff factor for the particular solution they are giving, and we'll be finding the osmotic pressure or the number of moles or volume, whatever it is. Now, table 1.4 depicts values of the factor I for several strong electrolytes. For KCl, just a second. Yes, for KCl, NaCl and MgSO4, I values approach 2 as a solution becomes very dilute and they dissociate completely. So KCl will produce K plus and Cl. Therefore, I will be equal to 2. NaCl also will produce Na and Cl, Na plus and Cl minus. As expected, the value of I gets close to 3 for K2SO4. Now looking into this table, oopsies, yes. Now looking into this table, values of Van Hoff factor I at various concentrations for NaCl, KCl, MgSO4 and K2SO4 are given. So all these values near 2 for NaCl, KCl and MgSO4. So when there is a question containing these solutions, we'll have to take I to be 2 on our own. They might not be giving the value of I each and every time if it is a solution which is known to us, right? And for K2SO4 it is nearly 3, so for our I value will be 3. This these values are these values of I are for complete dissociation, whereas for incomplete dissociation we have 1.87, 1.94, 1.97. Then it is incomplete dissociation. But when it is complete, these are the values for I. That's it. We come to the end of the chapter. We come to the end of the video also, line by line NCERT explanation. This was your first chapter, solutions. So thank you for joining us as we explore the fascinating concepts in this chapter. And I hope you found the explanations clear and insightful. So if you enjoyed this video, please give it a thumbs up and consider subscribing to our channel for more educational content. Don't forget to hit the bell icon so you can never miss an update. We'd love to hear your thoughts and questions in the comments below. Until next time, keep learning and stay curious.